So good morning, everybody. Today, Soeren will continue his lecture on non-equilibrium QCD on the lattice.
Yes, okay, good. So good morning, everybody. Welcome back to those of you who made it. So today we're going to continue our discussion on non-equilibrium dynamics. And so let's do a brief recap of where we got to this point. So we started with our construction from this non-equilibrium path integral in quantum field theories, and then derived this semi-classical approximation. And so what we did during the last course is that we actually went ahead and, besides looking at one particular example where this formalism is applicable, we somehow further analyzed the structure of the corrections to semi-classics, and based on that ground, sort of developed a classicality condition, which is again noted up here. Yeah? And so the essence of that condition is that we can use this semi-classical approximation to describe real-time dynamics of quantum fields whenever somehow the occupancy of bosonic quantum fields is very high, and very high means much larger than unity. And so this is in principle, as we discussed, just a simple manifestation of the correspondence principle, namely that somehow highly occupied quantum states exhibit classical features. And so, as we'll learn today, there's actually several interesting states of this nature in QCD, cosmology, and so forth. So the first example that we were about to discuss was this example of scalar field reheating, and so somehow basically going through a sequence of steps, we kind of argued that essentially this problem can be mapped onto studying thermalization of a scalar field simply in a static box. So just imagine you have somehow scalar particles, right, which are somehow in a box, right? And you want to understand how this system now thermalizes. Now, let me pick off back here, because that's somehow going to be essential to now the dynamics that we want to understand, right? And so, of course, if we want to study a non-equilibrium problem, first thing we have to say what is actually the non-equilibrium state that we're studying, right? And so, of course, in this example, somehow the motivation comes from understanding this dynamics that is or may be going on, may have gone going on in the early universe, right? Where somehow initially a lot of the energy is contained in this scalar field, which is somewhere sitting far away from its minimum, sort of at the top of its potential, right? And so essentially at the beginning, this is somehow very slowly starting to roll down its potential, right? So we have a very large scalar field expectation value, but a sort of a small momentum. So here eta, if you remember, was somehow the conformal time that we used to somehow map this problem in the expanding universe to the simpler problem of studying this in a static box. Now, as we had also discussed briefly, is that, of course, if you have a somehow classical scalar field, right, which is homogeneous throughout your entire space, right, then classically that would remain true for all times. So it's important to somehow consider the fluctuations that are actually present around that scale. And so the origin of these fluctuations is somehow really quantum mechanical, right? So, I mean, we know that in a quantum system, we cannot just have some homogeneous state across the entire space, right? There'll always be fluctuations around it, and these are really just vacuum fluctuations, right? And so within somehow the formalism that we had developed, right, where these things come in, they come in through this Wigner function, right? And so in Wigner-coupled theories, you can actually calculate the structure of what that Wigner function looks like. And so, so to somehow leading non-trivial order, right? These are simply given by somehow Gaussian fluctuations of the field, right? Which are now spatially inhomogeneous, right? So for instance, if you look at somehow the two-point correlation function of the field in Fourier space as a function of the momentum, right? And so you would basically have uncorrelated Fourier modes, and they have sort of a weight which is given by their quasi-particle energy. Now, before we go on to kind of see what has actually happened, and this we already discussed also, but this will be very important for what follows, so I'll go through it again, is let's first, oftentimes, right, if you're starting with a non-equilibrium problem and you want to understand sort of where the journey is going, it's good if you can actually find out what is the thermal state supposed to look like that eventually you're going to relax, right? Because you're starting with a far from equilibrium system. Typically, what you expect is that on long time scale, you'll eventually reach an equilibrium state, right? And so if you can already understand you're starting from here and you're going to there, well, then
it'll certainly be easier to understand what is going on in between, okay? So let's try and do that. So what is really somehow the characteristic feature that sets this initial state apart from the corresponding equilibrium state? Well, in the initial state, we have this incredibly large, somehow coherent length. Yeah? So the field that we're considering is really homogeneous. So it's somehow coherent throughout the entire system that we're considering. So this is somehow denoted here by the coherence length being on the scale of the system size L, right? So in the early universe, that would actually be the entire size of the universe at that scale. And so that is something that is actually very different from equilibrium, right? Because on equilibrium, we know we have all these, essentially equilibrium is dominated by degrees of freedom on the order of the temperature. That's anyway what dominates things like the energy density and pressures and so forth, so the most basic quantities. And so we have these kind of incredible sort of short wavelength fluctuations. And so you can, by somehow matching the energies, you can essentially map this out. On the one hand, what the final temperature of the system should be, and also what this coherent length should eventually become. But so the basic point is just really what one needs to accomplish for this system to thermalize is we somehow need a transfer of the energy that is at the beginning, all contained in that homogeneous field, into a lot of these sort of short wavelength fluctuations. So energy has to go from the field into the fluctuations on the one hand, right? And on the other hand, it has to go from somehow this being these very long wavelengths, excitation, right, which is the homogeneous field, to these incredibly short wavelength fluctuations, which are on the order of the inverse temperature. Okay, so now let's try to understand how this happens, right? And so, one reason for this is for choosing this particular example. You may say, okay, I'm here to learn about QCD. Why do I care about the scalar field, right? And that's to a certain extent perhaps right? But the beauty about this is a lot of the physics that's also relevant in different contexts, for instance in QCD, you can really understand very beautifully, and you can actually do a lot of sort of more or less analytic calculations in this context too. So I'm not going to present all of them here, but I hope you'll catch the essence. So, okay, so the nature of the problem that we have initially somehow is we have this large homogeneous field, right? And we have very small fluctuations around, right? And so in order to sort of get a first insight on what is going on at early times, right, it essentially screams for somehow treating this problem somewhat perturbatively, right? By essentially saying, well, okay, let's just look, okay, what happens if we only have this kind of strong field present, right? And then see how the fluctuations respond to the presence of that field. And so in that spirit, right, one can then split essentially the space-time dependent field, right, into somehow the spatially homogeneous average component, plus somehow the small spatially dependent fluctuations, right, which initially are just seeded by these vacuum fluctuations. And one can then essentially derive separate equations of motions on the one hand for this background field, and then the other hand for the fluctuations. And so if you work out the equation of motion for the background field, right, and that's just the scalar field equation of motion, since the thing is homogeneous, right, there are no gradient terms in here, right? And so in principle, this just takes this kind of simple, completely anharmonic oscillator form, up to somehow nonlinear effects, which characterize the back reaction of the fluctuations onto the background field. But as long as the fluctuations are small, we can somehow neglect these terms in the first go. And so you can easily solve this, right? So, the solution to this is just given by this Jacobi cosine function, right? So, I wrote it down over here, and so basically what this characterizes is just anharmonic oscillations of the scalar field in its potential, right? And so, okay, what this thing will do is it will start to roll down here, right? And it'll then somehow start to oscillate in its potential. Okay, good. So this is somehow, this is somehow easy to work out, right? But that does, in no way does that help us to somehow thermalize the system, right? Because all that's happening for somehow the background field is, right, it's just converting its potential energy into its kinetic energy and vice versa, right? But to really now meaningfully be able to somehow approach equilibrium, right, we need to look at what is actually going on with the fluctuations and how we can particularly transfer energy to the fluctuations, right? Because that's eventually what will need to happen. Okay, so within this decomposition, we can then go and work out now the equations of motions for the fluctuating field. So for these small fluctuations, right? And so again, right? I mean, you just start from where do we have the classical equations of motion? Right? Do we have them somewhere? Well, you start from the equations of motion down here, right? So this term we threw out, right? Okay, so you have a time derivative. Now for the fluctuations, you will also have gradients, of course, present. So we're dealing with these in momentum space, right? But now the anharmonic term, to leading approximation, will just involve the interaction of these small fluctuations with the background field, right? And so, okay, so if you expand this phi cube term, basically what you'll pick up is somehow essentially two powers of the homogeneous background field, which is then coupled to the fluctuations. Okay, so now what is the, and of course, as usual, right, there will be nonlinear effects here, which characterize the fact that, okay, I could not only pick up the background field here, but I could also pick up higher powers of the fluctuating field, right? Okay, but again, right, initially fluctuations are small, so we can somehow try to ignore these nonlinear effects in the first go. Okay, so then now let's somehow have a little bit of a closer look of this equation of motion and try to connect it with this picture up here. Okay, so anybody sees the connection between this equation and this picture here? Okay, good. Nobody? Okay, then at least I'm telling something non-trivial here, right? Okay, so what do we have, right? So basically this is, okay, so we have a second time derivative acting on our small fluctuation field, right? Yeah, and then so if I move this to the right-hand side here, right, then this basically looks like an oscillator equation, right? But now the thing is that, okay, it's somehow well, if you want, so the frequency of the oscillator, right, is also varying periodically with time, right, due to the fact that this background field is oscillating in its potential, right? So there's this harmonic change here of the background field in this potential, right? And so this is really completely analogous, right, to somehow having a person on a swing, right? But then what you do on the swing is, right, you kind of move your legs up and down, right? And by that, what you're effectively doing is you're changing your moment of inertia, right? So you're also changing your eigenfrequency of yourself, I guess, in that case, right? You're also changing that periodically, right? And as you know, right, if you do that well enough, right, your motion on the swing will accelerate, right? So it will lead to a growth in amplitude, right? And so exactly the same thing happens here actually for these kind of small vacuum fluctuations. So since their frequency is subject to a periodic modulation, and it's actually an anharmonic periodic modulation, this will lead to an amplification of these small fluctuations. And so in fact, this is associated with an unstable, with an exponential growth. And so you can, in principle, you can actually beautifully work this out analytically. So I think this is called the Lamé equation, or it's at least a variant of the Lamé equation. There's a lot of analytical work on this, for instance, seen in this paper. But so basically what you will find is if you actually analyze this equation, so you can look at this as a function of the wave number or momentum of these fluctuations modes, and you can define a growth rate. So the growth rate means that this mode, so how do I denote this here? Delta phi of eta and p will grow exponentially with a rate that's gamma p times eta, okay? And so what you will find is that there's a single unstable band here, which looks somewhat like this. So you have a maximum growth rate somewhere here, and then for a certain set of low momentum modes which grow, whereas the high momentum modes they are stable again. So for them somehow, if you want, so the intrinsic oscillation frequency is too large, to really efficiently benefit from this periodic modulation and thereby grow. Now, okay, so this is already kind of nice, right? Because this somehow provides, in the first step, a mechanism by which we can now transfer energy from the background field to the fluctuations, right? So the fluctuations will grow, at least a subset of them, right? And thereby pull out energy from this homogeneous scalar field. However, there's if you want to, then this immediately also leads to somehow a shortcoming of this analysis, namely, right? If you now look at some of these green brackets over here, right? Is in looking at these equations of motion so far, right? We've always neglected nonlinear effects of these fluctuations. And so that is fine as long as initially they're somehow small, right? But now we've just found that they somehow grow exponentially in time, right? And so in order to be able to somehow describe the dynamics beyond this very, very early stage of exponential growth, right? We then really have to take into account these nonlinear effects in the equations of motion, right? As they quickly become important in principle on a time scale, which is just given, well, which is given when essentially fluctuations become as big as the background field. So that's somehow very short time scale. And so this is then really where you have to somehow essentially switch from this somewhat analytic discussion over here, right? Which is nice to somehow illustrate the basic features of what is going on to the early times, to somehow take into account the full nonlinearities of the classical field equations in this case. But this can now be addressed within the simulation techniques that we had developed. Okay, so so how does one do this here then? And so this is essentially taken from this very beautiful paper by Misha and Katchev down here. And so, okay, so one now can study really what happens within classical statistical simulations of this scalar. So how does one do this in practice? And so essentially the numerics that one does are completely analogous to the scalar field study that we had discussed last time for an equilibrium system. Of course, the only difference now is that, okay, we have to consider this non-equilibrium initial state, right? So the question is, how does one set these kind of initial conditions? Well, okay, so we know what these initial conditions look like, right? We have this homogeneous scalar field, which has a large expectation value. And so if we look at somehow how to incorporate the initial conditions, then for the background field, there will be a component which is related to these to the expectation value of the homogeneous scalar field, and then there will be a component essentially representing the vacuum fluctuations. And so, as I said before, so these are essentially, so the vacuum fluctuations are characterized essentially by somehow a Gaussian correlation functions. And so the way that you can then essentially represent them in a simulation is now to essentially Gaussian random fluctuations of these fields. So essentially what this sum characterizes here. So this is again the quasi-particle energy, and these psi p are somehow Gaussian random numbers essentially multiplying each Fourier mode. And so of course now you have sort of a random component to your initial condition, right? So representing actually these vacuum fluctuations. And so, of course, the whole thing is then only meaningful under statistical averaging. But now, really what the statistical average somehow prescribes is just different microscopic realizations of these vacuum fluctuations that are present. Okay? So everything is the same as before in equilibrium, right? Where we somehow were characterizing thermal fluctuations statistically, right? Except that now in this setup, right, what we're actually characterizing statistically is these vacuum fluctuations that we're treating semi-classically. Omega p is still the quasi-particle energy. So that just comes from essentially, so that essentially just comes from writing a Gaussian density matrix around the scalar field. So you have this, so it's the quasi-particle energy in the presence of that homogeneous background field. Okay, so let's let's have a look at somehow what a typical outcome of a simulation looks like here. And so again, a lot of these patterns that I'm discussing here, they're really characteristic of somehow the dynamics of unstable systems. So this is an example that's particularly well understood, and you can somehow do a lot of things with a pen and paper as well, right? But so the basic feature that we're going to see here, you would also have for
unstable systems in say, non-abelian plasmas, say when you, for instance, have Weibull instabilities or something like this. And so that's why it's kind of good to look at. Okay, so we expect from somehow our linear instability analysis, right, that there should be somehow a subset of modes at early times which is growing, right, and so that should somehow lead to a growth of the fluctuations in the system. And so again, so indeed, looking at this plot, which is showing essentially two quantities. So the upper curve here shows the expectation value of this homogeneous background field that's actually averaged over one period of oscillation, right? Because otherwise this curve would be somehow all over the map due to the oscillation. So just showing the amplitude that is somehow multiplying this Jacobi cosine function, right? And on the lower curve, this is just the variance of the scalar field, which is somehow a measure of the integrated amount of fluctuations over all momentum mode. Yeah? So that's just the local variance in space, right? Which would be then the square sum of the amplitude of all Fourier modes. Yeah? And so indeed, what you see is that initially, right, you somehow start off with just having this huge scalar field, right, and somehow very small fluctuations, which are not even shown here, right? But then extremely rapidly, right, you have this growth, this strong growth of these fluctuations, yeah, so strong growth of the variance here, yeah, of course, due to the fact that the system is unstable, yeah, and it develops instabilities. Now, from the way I set this problem up, right, telling you that, okay, what we actually have to do, right, is we have to somehow transfer energy from the scalar field to the fluctuations and so forth, right, you may be actually tempted to think, right, that the instability is really what accomplishes this thing, okay? However, this turns out to be not true at all, okay? Namely, what this instability does, it only leads to growth somehow in this very narrow resonance band, right? So you populate sort of a certain subset of low-lying modes, right? But what you actually need to do in order to thermalize the system, you have to somehow move the energy somewhere away out here in momentum space, because the temperature of the system that you'll eventually reach is so large. And so this is essentially what will happen somehow in this later regime, which is then strongly nonlinear. So following somehow this fast early time dynamics in this linear instability regime, is then a very, very slow regime where now fluctuations are large, so field equations are highly nonlinear. But the system, even though this is somehow highly nonlinear, and you could think that, oh, well, okay, maybe the system here is very fast, very nonlinear, everything, right? The system actually evolves very, very slowly, and it evolves onwards towards equilibrium. Now, okay, so I've gone a little bit ahead of myself here, perhaps, right? I mean, you should challenge me on that claim. How do I see that the system here is somehow moving towards equilibrium, right? So, I mean, here I'm just looking at kind of two curves, right? I haven't really established any other properties of the system yet. And so, so somehow one has to find other ways to somehow quantify this non-equilibrium evolution further, right? And so what would be nice to somehow have, right, is, and that would be nice to have for somehow multiple purposes in a sense, right, would be to have a measure of somehow what are actually the states that are occupied at a given point in time during that time evolution, right? And because in particular we know then how this is related, how this looks like in an equilibrium state, right? Where in an equilibrium state, in principle, we should recover a Bose-Einstein distribution, for the states that are being occupied. Okay. So essentially what we want to now define or study is the concept of an occupation number, right? But now we want to somehow have an occupation number not in an equilibrium system, well, there it's kind of boring, right? It's just the Bose-Einstein distribution, right? But we want to have an occupation number in an out of equilibrium system, right? And so this is actually not really that well defined, right? So in principle, there's no unique definition of an occupation number in an out of equilibrium system, and you could explore somehow various definitions if you want, right? So one thing you could do, for instance, you could say, well, okay, in equilibrium I have this kind of relation, right? Let me just somehow
make this a definition also for the out of equilibrium system by saying, okay, I measure my statistical correlation function. That's something I could measure. I measure my spectral function. That's also something I could measure, although that would be more difficult, right? And then somehow the proportionality factor in between I would call an effective occupation number of an out of equilibrium system. Now, you could do that. That's fairly difficult to do, actually, due to the fact that the spectral function out of equilibrium is actually hard to calculate. So typically what one does is actually something different, which is on the one hand a lot easier to access, but also somehow has a relatively clear and nice physical interpretation. So the one case where we know we can very simply define an occupation number is in a non-interacting field here, right? Because there somehow occupation number, I mean, actually the occupancy of each state is conserved as a function of the time evolution, and all that will happen is that state will somehow have its standard e to the I omega t oscillation. Yeah? And so the perspective one kind of takes in doing that is that you say, okay, you have a non-equilibrium system which evolves up to a certain time where it can interact, right? And then you essentially instantaneously turn off the interaction and essentially look what then free streams into your detector. Okay, so that's kind of the type of measurement one actually does, right? Which in the context of, say, studying QCD or heavy ion collisions or so makes a lot of sense, right? You could always pretend that, okay, if no interaction happens afterwards, then things would just free stream into the detector. Perhaps in the context of the early universe, it's a little bit funny because we know the system has to afterwards go on and do a lot of other things. Okay, so, but basically what one does is one defines this occupation number by assuming that after the time of where we're interested in measuring the occupation number, no further interactions take place. And so if we do that, then we can basically solve free field equations of motion after the time that we're interested in measuring that, right? And so what that would mean is that afterwards somehow, well, the field could be decomposed into somehow forward and backward propagating plane waves, likewise the momentum field, right? And so by then somehow combining the field and its conjugate momentum field in Fourier space, right? I can basically map out these coefficients A and, well, in the classical theory, A star, in the quantum theory, this will be A dagger, right? And so, okay, the occupation number would then basically just be the expectation value of A star A or A dagger A, right? And so you can, okay, so there's a couple of lines of algebra to show that in order to be able to infer that, basically what you have to do is you have to take the Fourier transform of the field, subtract its momentum field divided by the quasi-particle energy, and that will give you a measure of the occupancy of these states. Yes? Excuse me?
In the expansion of phi, do you not presume any zero mode?
So the zero mode will actually end up as a large occupancy of the zero momentum state in this thing. Yeah. If you do it like that. But that's also not mostly what I'm after. Yeah, I'm actually mostly about somehow the ultraviolet properties of the theory in this context. There's a lot of interesting infrared physics actually going on in the scalar models. I'll say a few words about that. Okay, so So now we have somehow a more meaningful tool to characterize actually what is happening to that system. And so now let's look at this. Let's look at the evolution of this occupation number as a function of time. And so this occupation is so this plot that we're gonna be discussing now is really extremely characteristic for a lot of unstable systems. Yeah. So let's see what's going on. Okay. So there's different curves here, all of them showing somehow the occupation number as a function of the momentum, which is here normalized to the scalar field amplitude, because that's somehow the only dimensionful scale in the problem. Yeah, so the scale of these simulations is always set by the initial condition, and so in this case there was only one dimensional scale, which was the scalar field amplitude. And so what you can see, looking at these somehow very early times, is that indeed, as we had kind of cartoonized over there, right? There's somehow a range of low-lying modes, which starts to develop, which starts to become large. Okay, and now in principle, if you were to add more curves here, essentially what will happen is that somehow this mode starts to grow further and further until at some times, right, the interactions between between these unstable modes can no longer be neglected. And so what will happen then is then, as soon as, for instance, you can then basically have interactions between two unstable modes, which can lead essentially, for instance, to a fusion of their momentum, right? And so that will propagate these side bands of the instability. So that's when you start to develop somehow these very, very characteristic patterns of having somehow of somehow having additional peaks to this somehow linear instability, where, for instance, this sits here at somehow twice the characteristic. So this peak here sits at I think twice the characteristic growth of characteristic momentum of this band, and then 3 times and so forth, right? And so that just comes to the nonlinear interactions of these unstable fluctuations. And in fact, it turns out that there's actually this phenomenon which we call secondary instabilities is still something that in principle you could sort of understand semi-analytically. Now, at these early times, you have somehow these very complicated dynamics, right? And so lots of stuff's going on. I mean, this is a completely crazy looking spectrum, right? Like, I mean, if I ask you what is this supposed to look like, you would have never drawn this curve, right? Okay? But then if you go somehow towards later times, where really now these fluctuations have become large, and they have really become somehow on the order of the inverse self-coupling in the system. The coupling, I think, in this simulation is something like 10 to the minus 8. So the occupancy is really on the scale of inverse self-coupling, at least for low-lying modes. Something somewhat amazing happens, right? So you have all this crazy stuff going on at early times, right? But then if you follow somehow the system towards later times, things all of a sudden start to become amazingly simple again, okay? So all of a sudden you start to generate a relatively smooth spectrum, right? There's still some kind of enhancement here around this resonance peak, but other than that, essentially the spectrum becomes very smooth, and actually its overall shape or anything doesn't even change very much towards later and later times. So going here from something like 2500 to 10 to the 4, which is there's a huge time gap, right? If you compare it to somehow the time scales on which the spectrum changes at early times, really nothing much happens. The only thing that is clearly visible that is happening towards late time is that somehow this tail of the spectrum, right, that is somehow demarking this sharp fall off, that starts to move out towards higher and higher momentum. And so indeed that is somehow what we should expect that should happen, right? Because as I said early on, right, what thermalization for this system means to transfer energy from the low-lying infrared modes, so from somewhere around here, well, actually at 0, right, where the field sits, towards the temperature scale, which will be somewhere way out here, right? And so this is somehow realized by this what is actually a self-similar evolution. So what do I mean by this is a self-similar evolution? Well, so as already emerging from this plot, somehow this really actually very nonlinear dynamics at late times becomes surprisingly simple, and it is actually so it turns out that the spectrum that you find here beyond somehow these very early times, where you have the instabilities present, can be described in a mathematically very simple form, where actually the time and momentum dependence of the spectrum, in fact, does not appear separately, right? But it only appears in a combined way. So namely, essentially what you can do is you kind of see this by eye here, right? So if you take this spectrum and you kind of just shift it a little bit, right? This is essentially the same spectrum, right? It's just shifted over to the right, right? And somehow the amplitude of the thing is changed, right? And so indeed you can somehow, so mathematically the way you would describe this is you would describe this by somehow measuring the spectrum, say, as a function of a characteristic momentum scale here. So you would draw this as, they call this momentum scale lambda here, right? So then lambda would be a time-dependent scale. So you would draw the spectrum as a function of momentum over this characteristic scale lambda. And so it turns out that this characteristic scale evolves according to a power law, which is t to the alpha, okay? So this is the spectrum divided by its kind of characteristic momentum scale. And but then it turns out, okay, that in fact you also have to account for an overall rescaling of the amplitude of the spectrum, which again follows a power law. So this is characterized here this factor t to the gamma. And that if you do that, actually the simulation results towards these later times, they completely overlap. And so this is a little bit hard to kind of see on this picture, right? So instead, it's better to somehow look at moments of this phase-space distribution, right? And so here they actually did exactly this, right? So you look at now k to the 4, so you multiply with the 4 power of the momentum, then you get somehow a nice peak, right? So you get this sort of bell-shaped curve, right? Okay, so in this case, the bell-shaped curve moves out to the right and goes up a little bit, right? But then if you apply these rescalings, right? So trying to map out this stationary fixed point distribution NS, then what you will see is that you can actually take all these curves and sort of scale them onto a single curve, really showing the fact that this evolution is self-similar. And so this is something truly remarkable, actually, right? Because, essentially what you're saying is that, okay, so you have this very dynamical system, somehow on its way from this somehow far from equilibrium initial state to equilibrium, which is somehow parametrically a well-separated state. And instead of somehow, going there directly or taking some crazy route, right? It actually takes this route where somehow the evolution is quasi-static, that in the sense, you look at the system at a given instant of time, right? And you somehow say you measure correlation functions on a certain scale. Then you do repeat the same thing at a later time. What you're saying is that all the statistical properties of the system at the later time are exactly the same. All you have to do is you just have to essentially account for rescaling your resolution, taking into account this evolution of the characteristic Hart scale in the system, and rescale somehow the overall amplitude of fluctuations that you observe in the system.
So what parameters and initial conditions decide the time scale over which you can reach this?
So here the time scale is essentially set by the growth of the instability in this example. So it's basically determined by the time scale when the dynamics becomes when the dynamics of fluctuations become strongly nonlinear. So in this case, you have a field which is, or a background field squared, which is on the order of the inverse self-coupling. And then you have to ask yourself, when do the fluctuations become as large as that background field? That's basically when somehow the strongly nonlinear regime sets in. And so in that case, the time scale is just given by the inverse of somehow the maximal growth rate times the logarithm in the coupling, in the inverse coupling, in this case. If you were to start from somehow more smooth kind of initial condition, then it would typically given by the time scale of a single scattering.
So in this case, one more question is, is a systematic way to understand that your conclusions are not depend on the UV cutoff that you're imposing, the lattice cutoff?
Yes, there is a systematic way actually, right? Let me perhaps postpone the answer to this question. Perhaps you can ask this again in sort of 3 slides, and then I can probably comment more systematically on this. Yes? Yes and no. Actually, both of these questions, you may not realize this, but both of these questions are actually intricately related. And perhaps I'll postpone this for another couple of slides too, and then I'll come back to the answer of this question. Okay, yeah. So this is really interesting, right? So we started from something, some very complicated problem, and all of a sudden the answer turns out to be fairly simple, right? Namely, now, this is truly remarkable, right? So the entire dynamics at late times is somehow described in terms of essentially 3 very simple objects, right? On the one hand, there's somehow this scaling function, which describes somehow the spectral shape of this object that we call non-thermal fixed point. And so what does that look like? Well, it has some kind of infrared power law, which is actually non-thermal in this case. Yeah, so it has a spectral exponent of -3/2, right? Whereas the typical thermal exponent would be 1, and that's somehow also shown here for comparison, and then somehow steeply drops beyond this characteristic momentum scales. And it comes okay, so that is somehow just the spectral distribution of energy or
fluctuations in the system, right? But then really what characterizes the dynamics, so the dynamics is how essentially energy gets pushed out towards the UV here. That is actually just characterized in terms of these kind of two very simple scaling exponents, and you can extract these from the simulations, they come out to have approximately these values, -4/5 and 1/5. So essentially the hardening of the scale, so the maximal energy, so the scale up to which you have essentially be able to push out your energy content grows as time to the 1/5 in this kind of study. Okay, so now you may ask yourself well, okay, this all sounds very interesting, right? But okay, this was also somehow very peculiar problem that we started with. We somehow had this huge. You mean the equilibrium critical exponent? No. This is a different non-equilibrium universality class, if you want. So this is for n scalars, the dynamic universality class. You're going one and a half lectures ahead. Okay. Now, so you may ask yourself, okay, so this all looks very interesting, right? But okay, this was also somehow a very special state that we consider. We had this huge background field, right? I mean, how generic of a phenomenon is this actually? And it turns out it's actually very generic of a phenomenon, okay? So one first way to test this is, right, to stay within the same theory, right? But now just consider a different set of initial conditions, right? So for instance, instead of So that's something we actually did, right? So instead of somehow having, for instance, this huge homogeneous field, right, where you have instabilities and everything going on at early times, right? You could also say, well, what if I just start somehow with having, say, a large phase space occupancy in the infrared, right? So just somehow starting with an incoherent superposition of fluctuations, which are localized in the infrared modes, right? How does that evolve, right? And so we kind of played this game actually, right? Where we started once from a background field, right? Once we started from somehow distribution like this, phase space distribution like this, phase space distribution like this, right? And so what you can see is that you evolve this for a certain amount of time, right? The answer are given by these three curves here, right? And you can see that they're practically indistinguishable, okay? So here the energy density of the system is kept fixed, and that's actually important to somehow give these curves the same normalization. But really what happens is that during these early stages where somehow the system is very strongly nonlinear, either due to the fact that instabilities have somehow seeded strong fluctuations, or you have put strong fluctuations by hand, somehow interaction rates are so strong that the system actually very quickly forgets about the details of initial conditions and reaches this non-equilibrium attractor solution, which we call a non-thermal fixed point, which in this case is associated with an ultraviolet cascade, namely pushing out the energy towards higher scales, towards scales which eventually become of the order of the temperature. And so in a sense, this is not really surprising that this happens. I mean, perhaps that the memory loss happens is somewhat amazing, right? But I mean, the basic problem that you're facing, irrespective of somehow what are these different initial conditions, is really the same in all of these things. And in principle, this is a classic problem of turbulence, actually. Namely, you have this initial state which is far from equilibrium, where all the energy somehow sits in the infrared, right? And then what you have to accomplish to reach equilibrium, which kind of has the energy sitting here somehow in the low occupancy tail, is you have to transfer the energy out to larger scales, and this is achieved by this self-similar cascade, where somehow the maximum momentum that you reach at a certain time goes outward and outward. Now I will address the two questions that you guys asked. So in a sense, how is this now actually related to somehow thermalization? And can we describe this semi-classically? What is the role of the ultraviolet cutoff and so forth? So it turns out, and we'll actually see this probably tomorrow, is that in a classical theory, so in principle, this cascade would actually go on forever if the theory had no ultraviolet cutoff.
So the classical theory wouldn't know about this equilibrium state actually, because an equilibrium state, right, has an order 1 occupancy of hard modes, right? So I mean, at that scale, you cannot describe the system semi-classically. That's really a true quantum state, okay? And so what a classical system would actually do, it would kind of just run by this thermal equilibrium state and basically try to push out the energy further and further into the ultraviolet, trying to essentially explore all the phase space that's available to the classical system. Now, if you were to put a UV cutoff somewhere, then basically what the system would do is eventually this cascade would hit the ultraviolet cutoff, and that's when the system would thermalize, actually, classically, right? And that is related to the fact that, of course, a classical equilibrium state can only be well defined in conjunction with an ultraviolet cutoff, because otherwise you have this Rayleigh-Jeans catastrophe, right? I mean, the energy density of a classical equilibrium system is, it depends on the cutoff. I mean, otherwise you get divergent integrals. And so in terms of developing sensitivity to the cutoff in the simulations, which was Ayan's question, effectively what happens is that actually only somehow the low-lying modes are populated, right? And so basically if your lattice cutoff is somewhere out here, right, and somewhere far enough separated from your infrared physics that you're describing, then you can actually take the continuum limit of these simulations without being affected by the ultraviolet cutoff. All you have to make sure is that you don't push the evolution, right, further than when quantum corrections actually become of order 1, right? So when the system somehow becomes close to equilibrium, because that's ultimately when your semi-classical description has to break down, right? Because then you're really entering quantum land. Okay? And so that is essentially coming back to the fact that I alluded to earlier, right? That somehow this semi-classical, this classicality condition is a time-dependent criterion, right? And so it'll typically break down after some time of the evolution, even if the system initially was sort of very classical, right? And that's exactly what's happening here, right? So the occupancies at these tails, they somehow start to dip, and eventually they'll become small when you get close to equilibrium, and that's when you can simply no longer use this approach, right? And so that's sort of a general thing that emerges. Yeah? So in using these somehow semi-classical techniques, they're very powerful to somehow describe dynamics of far from equilibrium quantum systems when they feature strong occupancies. But as soon as you get somehow close to equilibrium, you know you're going to be dominated by somehow these hard quantum modes, right? Which are modes on the order of the temperature. And these are just simply never these are never classical, right? You can never describe them semi-classical. Okay, more questions here. Well, actually, I have one more thing to say. So one of the things you guys could have kind of objected to is that, I mean, so on the surface, these initial conditions, so studying somehow these 3 initial conditions is relatively similar, right? However, I mean, there's still somehow a difference, right? Because in the one case, okay, so they're similar from the perspective that for the system to thermalize, I have to transfer energy towards the ultraviolet, right? But they're yet different because one of them somehow features this homogeneous condensate, right? Whereas in the other, somehow the correlation length is large but finite, right? And so that's somehow clearly different, right? And so it turns out that actually, even if you start from initial conditions like this, there's actually 2 dynamics going on at the same time. Namely, it turns out that in addition to somehow having this direct energy cascade towards the ultraviolet, so thereby somehow transporting energy to the ultraviolet, and that's kind of what we argued to reach thermalization, there's actually an inverse cascade going on at the same time, whereby essentially you're moving particle number into the infrared. And so in a sense, there's somehow 2 of these what I call non-thermal fixed points, so these are these self-similar scaling solutions, realized at the same time, one of them associated with the energy transport towards the ultraviolet, and one of them associated with the particle transport to the infrared. And so this is due to the fact that somehow in these scalar field theories, actually particle number violating processes, they're strongly suppressed. So the time scale to somehow reduce particle number in these interactions is actually very, very large. So requires, I think it's suppressed by an extra power of lambda squared. So if the coupling is small, it's a very inefficient process. And so that means that somehow, even though ultimately in equilibrium, this excess of particle number that was there in the initial condition will disappear, there's somehow a transient time scale over which particle number can effectively be described as a conserved quantity. And so somehow the most efficient way to account for this excess of particle number is to put it into somehow the low momentum modes where it doesn't cost you any additional energy. Okay? Right? Because low momentum modes carry smaller energy, so you put it there. And so this has an interesting consequence, actually, that if you consider somehow a finite size system, right, then eventually you'll somehow push the particle number further and further into the infrared until you actually reach again a coherent state in that finite volume system. And what that means is essentially that you're Bose-condensing these relativistic scalar particles. And so this is really, I mean, this is a true out of equilibrium phenomenon. In equilibrium, this cannot happen. This is not a conserved charge. There cannot be a Bose condensate in a relativistic scalar field. Nevertheless, if you somehow you look at the condensate amplitude, so this is now again somehow showing these three simulations I had on the previous slide, right? So you look at this somehow starting from a background condensate, right? Or you can start it from just having strong fluctuations in the system. Then what you will find is that somehow in a finite size system, after a certain amount of time, you will again establish actually this homogeneous condensate. And so this is really, really remarkable property. Now, of course, if you go to very, very large systems or in the limit of infinite systems, then to establish a condensate, you have to essentially establish a correlation length which is on the order of the full system size for these modes. So you have to establish long-range correlations over the size of the whole system. And so causality already tells you that this should somehow take an infinite amount of time if you make the system infinite, right? So there's an obvious causality bound. This turns out in fact, the bound that you actually get from the dynamics is stricter than the causality bound. And so what you find is that in the infinite volume limit, so this is now comparing simulations at a different volume, looking at essentially the occupancy of the zero mode, which is what you would call the condensate, so in small volumes you do form a condensate, which then somehow remains constant as a function of time. But as you go to somehow larger and larger size systems, essentially this time when you reach condensation would diverge as a function of the volume. And so in principle you can. So again, this is described by a self-similar infrared cascade, and you can map out actually what is the power of the divergence with the volume. I think it's. I don't know the exponent off the top of my head, actually. Okay, so questions on the scalar part here? Yes.
Regarding your definition of the occupation number, so did I get you right? You're assuming that after the time of interest, there are no further interactions, so you have a well-defined occupation number, and you just take that one.
Yes.
But how do you justify this idea that there are no further interactions after this time? I didn't quite get that.
Well, I want to know a property about the system at a certain instant of time, right? And so, one of the downsides indeed of using something like that is, right, you would have to do a Fourier transform with respect to relative time. So essentially what you would measure would not be somehow the state of the system at a given time, but you would also somehow include its past and its future history, right? So this is essentially a nice definition, because it really tells you about the properties of the field on a given time slice, if you want so. And that's really what you want to, what I think you want to characterize.
I see.
Unequal time correlation functions are also interesting in principle because they somehow tell you about, like the spectral function also tells you about the nature of possible excitations in the system and so forth. But they somehow carry a different information content, essentially. So in a sense, what I want to characterize, I just want to characterize the field in terms of its correlation functions on a given time slice, but then it's sort of nice or intuitive to interpret this in terms of an occupation number by using this free field decomposition, and that exactly corresponds to doing this kind of measurement where afterwards you just free stream them into the metadata.
I see. Thank you.
Further questions? Okay, I don't see any. So then,
let's move on. And so now we've discovered somehow this really exciting non-equilibrium phenomenon here, right? But we've still been doing scalars, right? We're here to do QCD, right? And so the question is whether we can somehow find something similar also, for instance, in gauge theory, okay? And so actually, and this is actually sort of loosely relevant to the study of high energy heavy ion collisions in the weak coupling, right? So as Raju discussed very nicely, right, within this description of heavy ion collisions in the CGC effective field theory, right, you basically have somehow these somehow strong static Koller sources which sit on the, which are confined inside these thin sheets of the nucleus, right? And then okay, so as these collide, essentially they pass through each other, right? But they leave behind this debris of these very strong fields, okay? So there's this strong field somehow mediating the interactions between quarks and gluons inside these nuclei. And so again, these fields that you have initially, they're created with a very large phase space occupancy, right? Which is also in this case is non-perturbatively large. It's on the order of 1 over g squared. And so again, the logic is that if we have this, if we have occupancies on the order of 1 over g squared and g is very small, then that's a large occupancy, right? So we can use somehow semi-classical techniques to describe the early time dynamics. Now, I should make an important point here is that one very important aspect of somehow studying this problem in heavy ion collisions is that immediately after the collision, the system is subject to this rapid longitudinal expansion in the beam direction, okay? And so that really plays a super important role in understanding the properties of what is going on during the early stages of heavy ion collisions. But in what's going to follow, I'm going to neglect that longitudinal expansion, right? And just to somehow have a sort of a simpler setup first, right? I'm going to talk about somehow how does actually a plasma of gluons, okay, thermalize in a static box, right? If I set it up in a similar way as I did this cosmology problem. We've also looked at the other problem, but just a whole lot more complicated, and this is something nicer and somehow gives a conceptually clearer picture. Okay. Okay. So now. And we want to look at the dynamics of gauge theories, right? But okay, so we have to somehow adapt our formalism now to gauge theories, okay? And so, there's a couple of new things that come into play here, right? Which we have to at least briefly discuss to be able to somehow now study non-equilibrium dynamics of gauge theories. So if you remember, right, we had this kind of cookbook recipe on what we have to do to study real-time dynamics in classical statistical approximation, and step 0 was to discretize the theory on a lattice, right? So far this has been trivial, right? And the reason that this has been trivial for the scalar field theory is that because the scalar field theory didn't have any really important symmetries that we had to preserve in the lattice discretization. And so this is different, of course, for gauge theory, right, which has a local gauge symmetry, right? And that local gauge symmetry is clearly something important, right? It's and so we want to preserve that when we go to a lattice discretization, okay? And so the common solution to this, and of course I didn't invent this, right? This is the machinery of lattice QCD. So probably Peter talked about this as well last week, right? Is to actually not work with the gauge fields as your degrees of freedom, but instead as your degrees of freedom, you choose these Wilson lines, which are, well, as Edmond discussed yesterday, which are just path-ordered exponentials of the gauge field along a certain path. And so the way to do this is to, okay, so you set up your system on a lattice, right? So you have lattice points xi plus 1, blah, 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 blah. And okay, so you define, so what you define as your interesting variables is essentially the path order, so is essentially the Wilson line connecting this point with this point. So from here to here, okay, along a straight line path. And that's the variable that you want to keep track of, essentially. Now, why is this nice? The reason that this is nice is that, okay, the gauge field has somehow complicated transformation rule under gauge transformations, in particular involves somehow derivative of the gauge transformation, which, derivatives are notoriously bad if you're dealing on a discretized space, right? In contrast, this Wilson line under gauge transformation only knows about its beginning and end point. And so if you have a lattice, right, then okay, you should be knowing what's going on at the beginning and the end point, right? And so then working with these Wilson line variables is actually what allows you to somehow, instead of having a continuous gauge symmetry at sort of every at continuous points in space and time, right, to retain a discrete gauge symmetry at every point on your space-time lattice space. Okay? Simply because you're working now with these Wilson lines. Okay, so now how is this? How is this related to what we want to study? And so, I mean, okay, of course, right? Eventually, you have to somehow make your lattice fine enough, right? And so, sufficiently close to the. So, of course, if you're sufficiently close to the continuum limit, then this path will be very short, right? And so, along a very short path, right, you shouldn't be picking up much of a phase or much of a color rotation that is encoded in these Wilson lines, right? And you can basically expand this path ordered exponential, right? So, okay, it's roughly given by the exponential of the gauge field in the center of this link, right? Or you can just also expand it to somehow linear order, right? And then it would actually reproduce the gauge field. So that's if you now would be wanting to measure a gauge field. Okay, so now then, so that is somehow the relation to the continuum variables. Now, okay, so we know now the variables that we want to work in, right? So now the next thing we have to do is we have to somehow write down an action or Hamiltonian, and so the way we write down this action or Hamiltonian, it should of course be gauge invariant under this discrete set of gauge transformations at each space-time point. And so in principle, there's kind of two formalisms that you could choose. You could choose an action formalism as is conventional in lattice QCD, simply because you're dealing on a 4-dimensional lattice, and typically temporal and spatial spacings are on the same order, right? As we had already discussed for the example of the scalar theory, right? in this classical statistical real-time QCD, it's often the case that we usually want to have temporal spacings being much smaller than spatial lattice spacings, right? So meaning we take a small time step when we solve our equations of motion. And so for that reason, it is often convenient to work in the Hamiltonian formalism. Now, to define the Hamiltonian formalism for gauge theory, you actually do have to fix one gauge. And so what one usually does is one fixes the axial gauge in the time direction. So for the static box, this would be A0 is 0 gauge. For somehow a system that undergoes Bjorken expansion, this would be A tau equal to 0 gauge, but formalism is essentially the same. And so okay, I mean, fixing that gauge basically means that if you now look at somehow how our gauge fields would transform, right? So we want to set this guy to 0, well, then we can only consider time-independent gauge transformations. Because we have already used sort of one gauge degree of freedom to essentially fix that gauge. Okay? So what one then, so the task then becomes is now to build a Hamiltonian which is at least invariant under the residual gauge symmetry, which is that of time-independent gauge transformation at each lattice. Okay? Okay, so how is this done? How is this then discretized? So okay, so in the in the Hamiltonian formalism you have fields and momenta usually, right? So in this case the conjugate momentum variables are given by the electric fields, and you kind of multiply them by power of the gauge coupling and some powers of the lattice spacing to essentially make them dimensionless. And so under these time-independent gauge transformations, they basically just transform under the adjoint representation. Now, what is the Hamiltonian? Well, the Hamiltonian is 1/2 E squared plus 1/2 B squared, right? So the other thing that you need is magnetic fields. And so these magnetic fields, they're basically built out of, so they are built out of the gauge fields, right? So that's what it would be like in the continuum, right? So now we have to build them out of these gauge links. And so this is achieved to this kind of a plaquette. So you must have seen, I don't know how extensively Peter talked about this, so I'm just gonna say, doesn't matter to hear the same thing twice, right? Okay. So you have these gauge links, and so what you can do is you can basically form a closed loop of these things, right? And the closed loop essentially, what is a closed loop, right? So closed loop measures essentially the magnetic flux to that area, right? That's also a concept that's somehow familiar, right? And so if you work this out mathematically, right, then what you actually find is that if you take the trace of this, so the trace of such a Wilson loop, then that's roughly proportional to the magnetic field string squared up to some coefficients that you have to work out. What is? These are so SUNC gauge fields. I mean, you can do it for U1 also. For U1, in principle, you wouldn't have to do it. Now, what's the good property about this, right? So we said, how do these things behave under gauge transformation? They kind of behave
gauge transformation here, inverse gauge transformation at the endpoint. That's how a Wilson line transforms. And so if you form this closed loop, then basically the product of the successive links will cancel the gauge transformation at each of these intermediate points, and the whole thing will just gauge transform under the adjoint representation at the point that it's defined here. And so then if you take the trace of these things, then you can cancel this guy with this guy. Likewise, if you take the trace of E squared, you can cancel all the things here. And you end up with a manifestly gauge invariant lattice Hamiltonian, which is then basically E squared plus these plaquettes over here, which gives you P squared. Okay? Good. And so this is accurate. So I think this is accurate to order A squared in the lattice space. In principle, you could now, if you wanted to improve upon that, I would have to add somehow rectangles and boxes with larger areas, and then you could somehow cancel out higher order corrections and make this even more sophisticated. Okay, so now we have a Hamiltonian, but we still have to get equations of motions, right? And so in order to be able to do that, we actually have to, so what one in principle just has to do is, right, in principle, these are Hamilton's equations of motions, right? But there's one more thing that you have to do in this formalism. You have to actually define, right, what you mean by the variation of the gauge link with respect to the gauge field, because the gauge link is not really a canonical variable, right? The canonical variable would be the gauge field. So you can define that. You basically just say, okay, if I change the gauge field at a certain point, right, that's going to change the gauge link at that point, right? And then you obtain Hamilton's equations of motion as usual, and you can solve them, okay? Good. So that gives us the equation of motion. The next thing we need is initial conditions, okay? And so, as we had seen from the previous example of the scalar field, right, details of the equations of motions are most of the time irrelevant, okay? So, with that, we can just choose something simple, essentially, okay? And so, I mean, okay, you can cook up a lot of things. They're basically, I mean, at the end of the day, they're essentially all going to do the same thing, right? So what one typically does is actually one just uses somehow an incoherent superposition of free field modes. And so at the level of the gauge fields, so basically you can write it like this. So the free gauge is so a gauge field with in a fixed gauge would have an expansion like this, right? So now, in addition to somehow the usual Fourier phase, right, you have these polarization vectors in a given gauge. Typically, we like Coulomb gauge in this context. And then to somehow realize a state of a certain occupancy, we basically represent, so this combination of variables here would be like A, and this times, well, whatever is in the complex conjugate would be like A star, right? So we realize somehow Gaussian correlations of A and A star for each mode. And so the proportionality factor is then just the occupancy of the gauge field, or the occupancy of these modes at initial time. And so they're then realized basically by, similar to these vacuum fluctuations, right? In the case of the vacuum fluctuations, this was just one, I guess, or a half. I don't really know. I think a half probably. We now have an actual physical occupation of these modes, which is given by the square root of the initial occupancy. Now, there's one thing which is which requires here some special attention also, which is related to the fact that, okay, if we actually want to simulate a physically meaningful system, right, we should satisfy also the Gauss law, which tells us that somehow, okay, divergence or covariant divergence of our electric fields, right, is related to the charges in the system, right? So in this case, we are only talking about gauge fields, right? Gauge bosons, right? So there are no charges in the system, right? And so what that means is that essentially the divergence of these electric fields should be zero, right? And so this is, by the way, how a covariant derivative is discretized on the lattice. So it's kind of just taking a finite difference rule, but then you always have these parallel transporters by these gauge links. And so it turns out that if you work this out, actually what the equations of motion guarantee is that if this constraint is satisfied at a certain time, it'll be satisfied at any later time, because you can show by the virtues of the equation of motion that the time derivative of this Gauss law constraint is actually zero. But you still need to make sure that actually the initial conditions satisfy this constraint. And so if you just choose something like this, it will actually not satisfy this constraint. So by virtue of somehow choosing the correct polarization vectors, you will somehow satisfy Gauss law constraint in the free theory, so replacing the covariant derivative with an ordinary derivative, but not in the convariant way.
And so typically, typically you have to do something more. And so what you usually do is you actually minimize the deviation from the Gauss law constraint. So you set a set of initial conditions first, which violate Gauss law, but then you fix that up essentially by minimizing the absolute value of the violation via a gradient descent. So that's typically a very minimal modification of the initial condition, but it's somehow required for consistency of this analysis. Okay, so then there's the last point. So now, of course, now we have initial conditions, we have equation of motions, we can evolve our system, right? But now we also want to measure something, right? I mean, otherwise, why do we do this, right? Okay, so what can we measure? And so there's different things that we can measure. So of course we can measure gauge invariant operators, and that's at the end of the day what we should be measuring, right? And so, okay, then the strategy is just we have to express all these gauge invariant operators in terms of our lattice variables, make them invariant under this residual gauge symmetry that we have. And so there's a few things that you can easily measure. You can, for instance, measure the energy momentum tensor, or just energy or pressure, or something like E squared or B squared or something like this. I mean, these are natural gauge invariant quantities. You can also measure Wilson loop, right? So the smallest Wilson loop would be this elementary plaquette, right? But you could also measure some kind of bigger guy, say, for instance. That would also be easy, right? You would just somehow multiply all these plaquettes and so forth. And so that also contains an interesting. Now, to somehow study the dynamics, what we discussed previously, really what we are interested in to a large extent would be to extract something like an occupation number, right? And so that's somehow a non-trivial task, right? Because occupation number is based on correlation functions of the fields, right? And so if I just somehow look at a correlation function of gauge fields, then this is really not a meaningful concept, right? So I can make this a meaningful concept by either fixing a gauge, right? Because, I mean, so why is it not a meaningful concept? It's not a meaningful concept because it's not gauge invariant, right? So I would either have to fix a gauge, or I would actually have to consider a correlation function which is gauge invariant. And so this I could do by, for instance, adding a parallel transporter in between. So I could look at something like EI, then I have so pictorially I could measure my E field here, then I put a parallel transporter in between, measure an E field here. Well, I actually have to assess the adjoint parallel transporter and then parallel transport back, right? And then so this is again essentially a closed loop. Therefore, if I trace it, it's gauge invariant. Now you can do this. We've actually done this to a certain extent too. However, what's most frequently used is to actually use these gauge fixed correlation functions. So we've had somehow someone had quite good experience with this. And so, but then of course what one has to do is one has to fix a gauge, right? And so, okay, usually what one does is one exploits this residual gauge freedom that we have, namely to perform time-independent gauge transformations, to fix a physical gauge condition at the time when we want to measure the occupation, okay? So each time you measure an occupation number, you fix a gauge condition, like say Coulomb gauge, okay? Which is then valid at exactly that particular time when you measure, but at no other time. Okay, at the other time you only have axial gauge. Okay, so this is actually quite interesting. So how does one actually fix? A gauge on a lattice? And so this is kind of cool, actually. This is why I'm putting it here on the slide, because what you actually exploit is the fact that Coulomb gauge or I mean, all these gauges which are defined somehow by gradients, they exploit the fact that these are minimal gauges in the sense that if you take, for instance, in the continuum, right, you take your spatial gauge field, okay, you square it, and you sum that over all components and integrate that over the volume, then this will be minimal. So you have kind of the smallest possible fields representing a given physical state if the system satisfies Coulomb gauge. And so you can, so likewise on the lattice then, right, you can basically look at, okay, what is AI squared? Well, this is roughly given by the trace of 1 minus the plaquette, and then another minus the plaquette minus the links, right? And so you can define basically a gauge, so a gauge fixing functional, which is this guy over here,
which you can then optimize essentially to find somehow the smallest possible values of your gauge fields, which should then satisfy the Coulomb gauge. And so indeed, so you can, what you then do is you basically, again, optimize this by gradient descent. So you can now take a derivative with respect to performing a gauge transformation. What you will get back is you will basically get the gauge transformed links at one point minus the gauge transformed links at another point. And so now, remember, you can expand the gauge link in terms of this thing over here, right? And then so what you'll find is that at the stationary point, basically what this becomes is that somehow the discrete derivative of the gauge field is 0, which is exactly the Coulomb gauge condition, namely diAi is equal to 0. Now, one should note that so even with this gauge fixing, this is actually not unique, right? And so this is of course the famous Gribov problem, right? So in principle, what you find with this kind of thing is you're going to find a local minimum of your global gauge fixing functional, which will actually which will be it'll be a minimum, right? And it will satisfy the stationary condition, which is the Coulomb gauge, but it's not going to be, for instance, the global minimum in general. And so in principle, there can, if you want to be different, so there can be different Gribov copies, if you want, of the same gauge, and this will affect the correlation functions that you measure in principle. Now, you can study this, and so really what it turns out, it can actually relatively strongly affect the infrared modes in your system. So if you look at a typical spectrum, right, you shouldn't trust your very infrared modes, but somehow the effect on the hard modes is absolutely negligible. But so if you really want to go ahead and explore the infrared modes in a gauge theory, then somehow basing this on gauge fixed observables generally does not appear to be a very good idea. Let's put it like that. I've actually really seen examples where you fix different. You fix the same gauge, you end up in a different copy, and then you really get very different results for the spectra and infrared. Okay, so now we have then all the technology at hand to actually somehow study this problem. And so let's look what happens. Okay, so let's look what happens in the gauge theory. And so this is now analogous kind of simulation. So here we again, choose the initial state in a similar way. So we kind of put here, I think this should be on the plot. So actually the box goes to 1. So we put a very large occupancy here somehow in a low momentum range. And so again, what you find is that the dynamics is extremely similar to what we saw in the scalar theory, namely at early times. So the dynamics at very early times can actually depend strongly on the initial conditions. Also in gauge theories, you can realize various kinds of instabilities, viable instabilities in anisotropic systems, or magnetic instabilities like Nielsen-Olesen instabilities if you have very strongly coherent fields, for instance. And so at early times will depend somehow relatively strongly what your initial condition was, and it's kind of obvious, right? But then as the system evolves, you again reach this kind of cascading state, right, where the energy is transported towards the ultraviolet, right? And so in a very similar fashion, it's somehow described by an infrared power law, and then drops very steeply. And so as the system evolves as a function of time, right, this kind of front is pushed outwards while its amplitude decreases. And so again, you find this approach to this non-thermal fixed point, which again is characterized by a self-similar scaling behavior. So now here in this case, I actually made the plot myself, so this is actually somewhat easier to see what's going on. So the dotted line is the fit to a power law here. And so it turns out, there's actually the spectral slope of this thing. This is something that's somehow not really been fully clarified. So within the range where we can do the simulations, we find some exponent which is relatively close to 4/3, and that's in principle an exponent that you could expect from kind of a scaling analysis, although it doesn't exactly make sense, actually, to tell you the truth. Simulations based on kinetic theory, they seem to suggest that the fact that one observes 4/3 is due to the fact that somehow soft scales and hard scales in the system are not really that well separated at the times when we can do these simulations, and that it should somehow flatten out a little bit more as a function of time, but very, very slowly, because basically at soft scales you still have some, you have screening phenomena present and so forth, which then kind of slightly modify the shape of that distribution here, and so we kind of lead to sort of a slow evolution of this exponent as a function of time as the scales really become separated. Okay, but so really what you see again is this characteristic behavior of this non-thermal fixed point. So you again have such a self-similar scaling, and so here actually this is shown in what I find somehow a more transparent plot of this thing. So you can now actually look at somehow the spectral decomposition of the energy, if you want so, right? Or in this case, the quasi-particle energy, right? And plot that at different times, right? And so what you will see is, okay, that the energy is somehow always concentrated at this shock front in the spectrum, if you want so, right? And then as you, last couple of slides, and then as you kind of go on further, all that happens is that somehow this bell-shaped curve essentially translates out to higher and higher scales, and thereby really transporting the energy towards the ultraviolet, right? So in particular, you don't have to adjust normalization here or anything. And obviously this is somehow self-similar. Now in this case, it turns out that while somehow at the surface it's exactly the same, right? The scaling exponents that you find in this case are actually quite different. So they turn out to be these 4 7s and 1 7s, and so the ratio between the two is the same, but actually somehow how fast energy is moved towards the ultraviolet is actually different in the gauge theory as opposed to the scalar theory, and that's something we're going to discuss next time. And of course also the shape of this curve is different, but that somehow should be expected. Now this is the analysis based on spectra. I should say that in principle the same kind of scaling properties, and this is actually very important, can also be established on the basis of somehow looking at local gauge invariant operators. Okay, so if you just care about somehow what is sort of the characteristic hard scale in the system actually, right? You can in principle quantify this through a local gauge invariant operator, and so one of the things you can do is you can just look at di Fij squared and divide this by Fij squared, right? So you look at the ratio of a dimension 6 operator over a dimension 4 operator, okay? That should somehow give you the characteristic hard scale in the system squared, right? So if that's true, then this should somehow scale as the hard scale in the system, which is characterized by this exponent alpha, so it go as t to the 2 alpha, and so indeed you can kind of do the measurement here. Unfortunately, you cannot see the fit curve, but we actually took the logarithmic derivative here, and so you can really see nicely how this scales and how you pretty much nail down the scaling exponent with this kind of analysis. Okay, so this brings me to somehow wrapping this up, right? So what we've somehow uncovered today is a very interesting pattern about the thermalization process in this far from equilibrium system, and so that's somehow very different from things that we used to in somehow thinking about near equilibrium systems. Right? So usually when we think about a near equilibrium system, we say like, okay, well, system's somehow out of equilibrium, right? What will happen is we'll kind of just relax towards equilibrium on some time scale due to some exponential relaxation, right? So this is essentially the essence of the relaxation time approximation, for instance. However, it turns out what actually happens, or what can happen at least in this far from equilibrium system is really quite different, right? So if you look at a far from equilibrium system, you can find this phenomenon that very early on there's somehow an effective memory loss, right? And then the system really spends a long time in the vicinity of these non-thermal fixed points where you find these self-similar scaling behaviors. And so this is really related to the fact that somehow the initial state you're considering here is really parametrically different, if you want, so from the equilibrium state. For instance, the temperature in the system would be related to an inverse power of the coupling times the hard scale in the system initially. And so you have this pattern where somehow instead of sort of going directly away, towards equilibrium, you spend a lot of time at this fixed point, and you find this very interesting scaling behavior. And so I've shown you 2 examples now from essentially QCD, and in cosmology, it turns out there's similar behavior also going on in cold atom systems, for instance. And so
what we're gonna look at next time is then really what is the origin of this phenomenon, and right, like, I mean, we're getting this somehow surprisingly simple behavior based on our simulations, right? Is this something that we can really understand better, yeah? And what is actually, so what is actually really the role of this in the thermalization process? Yeah? How can we use this somehow, say, to, for instance, determine the thermalization time in the system? Okay, that's it for today. Thanks.
Thank you, Soeren, for this lecture. Is there any questions?
Since your entire philosophy is solving classical equation of motion, you have somewhere to take the A going to zero limit. And you said that your energy in cutoff actually is something that you cannot really remove. Everything goes in the same direction. So in what sense is this a complete picture?
So what do you mean? So what do you mean by a complete picture? So in the sense that...
I mean, if we go back to the picture where the question Ayan asked about the lattice spacing dependence.
Yeah. So okay. So there's two things. So let me try to explain this on the board actually, because this is really an important point, and this is also where there's a lot of confusion in the literature often actually. So. Okay, so you have to. So the first thing you have to is okay. So the first thing you have to ask yourself is how do you actually set up this simulation? Okay, and that then relates to the question of. Is this theory, well, is it finite? Are there problems with the lattice cutoff? Blah blah blah. Okay, so the way I would argue you should set up the system is you set up the system in a finite way. Okay, so in a classical theory, right, all that enters in loops and so forth are only the statistical fluctuations that are actually present in the system, right? There are no somehow quantum effects unless we put them by hand, okay? Unless we try to model them to sort of small fluctuations in all the ultraviolet. So the way you can set up the system is you set up the system in terms of the spectrum, right? So let's do this here as this n of k as a function of k, say, right? You set up the system as a spectrum, right, which really has a finite support, okay? Right, so it only has support up to a certain momentum scale, okay? Now, what will happen then is, as I said, right, is you will develop this cascade outwards here, right? And so if your system has a cutoff, then eventually what will happen is at some point that cascade will hit the cutoff, and then it will classically thermalize, okay? And so that's actually the point when you would start to become sensitive to lattice dependence and so on.
Yeah, I think that is where I object, because I think when you say that you are putting that cutoff, you have two roles for the cutoff. One is to solve your equations, and second is so you have a box, you have a lattice size. So this particular cutoff that you talk about is an ultraviolet cutoff.
Yeah, this is pi over A.
Yeah. So if that is really the case, and the equations that you set up, which you said you are going to discretize, with the assumption that you are going to really send A to 0 sometime.
Yes.
So if I send A to 0, then that cutoff goes to infinity.
Absolutely, and that's what I argue you have to do, right? Exactly, yeah. So let me carry on, right? So if you have a cutoff here, then at some point you will hit the cutoff, right? And clearly, once you become somehow close to the cutoff, indeed, right, you will have large errors in your equations of motions. You can no longer really describe continuum physics, and that's what's going on. Now, if you send that cutoff to infinity, so let's put infinity. No, we cannot cross this. Let's put infinity here, okay, right? Then what will happen is that somehow this classical cascade will just go on forever and forever, right? That's what's going to happen, okay? Now, is that physical? And the answer to that question is clearly no, right? Because we know eventually, right, our occupancies here will become small, right? I mean, you see the occupancy is going down, right? And that's when we can no longer ignore quantum effects, okay? That's when intrinsically this classical statistical approach breaks down. The problem is it doesn't know about its own breakdown, right? We have to monitor it ourselves, right? And convince ourselves that what we're doing still makes sense, okay? Yeah. So as long as somehow the occupancies here of the typical modes we're describing, right, remains large, we're doing a decent job. But when this becomes of order 1, then it means that after, I should really use multiple colors.
that after this time here, right, I should somehow not trust this classical simulation anymore. It doesn't make sense, right? So basically, so basically, if this is 1, right, I could perhaps follow the evolution of that system semi-classically, say up to something like here, right? But I would then have to switch my theoretical description, right? Because classical approximation no longer makes sense. Occupancies are not large. So what turns out to be the case, though, is that, at least for instance for the gauge theory, when this happens, so when the system actually becomes dilute, this characteristic hard scale here is already on the order of the temperature. So you have actually accomplished this task of transporting energy towards the UV, and then you essentially have a close to equilibrium system, but a close to equilibrium system which is quantum.
The fact that it is becomes temperature is presumably simply related to dimensional arguments and nothing to do with thermalization.
Well, actually,
and also, if the cutoff has to be maintained in order to make sense of the fact that thermalization is happening, how do you know that in continuum it is happening at all?
No. So I don't know. Perhaps I didn't explain this one. No. The point is the approach has a limited range of validity in the amount of time I can run it to, right? And for that time, I can send the cutoff to infinity, okay? But anything that happens after that time doesn't make sense to describe classically anyway. So it doesn't matter whether the system thermalizes classically or not or anything, right? It should never thermalize classically. I mean, it's nothing I want to study, right?
I'm not convinced, but anyway, we can continue this.
Further questions?
Yeah. So, I mean, till now I didn't have, but this statement you said that systems should not thermalize classically. What does it mean?
Well, I mean, so it means the following, right? So a classical equilibrium state, right, is only defined in conjunction with an ultraviolet cutoff. Okay, right? And so that comes from the simple fact, right? So I calculate the energy in the classical system, right? So this will be ddk T over omega of A, say, right? Up to some cutoff, and this will go as what? So this will be T times cutoff to, I guess, D minus 1 or D, something like this, whatever. Okay, right? So so D equals 3, right? This will be T times lambda cubed. Okay? Meaning, okay, the classical equilibrium that I can define, right, is only well defined with a cutoff and depends on somehow the cutoff scale I choose. Now, that's nothing that we have in a quantum theory, right? In quantum theory, we can define equilibrium without, in the continuum limit, right? Without having a cutoff. And so therefore, all it means is that for a classical system to thermalize, it has to hit its cutoff. But that's not a theory that we want to study, right? Because then we're somehow studying a theory with a cutoff. It doesn't make sense.
Further questions? So if there are no further questions, let us thank Soeren again.